Now, okay, that's a definition. Here's an example. Okay, that the expected height, if you're talking about men, is the expectation with respect to the probabilities updated to the fact that you have new information that it's a man in the outcome, and if you do it for women, it's new information that it's a woman in the outcome. Okay, now the law of total probability allows us to compute expectations in a very convenient way, just like the law of total expectation allows us to compute expectations in a convenient way, just like the law of total probability. So the law of total expectation. Okay, now this is very important. Because why? Because at the beginning of the lecture I said the expected value is very important. That's why Orange Malik showed up, because now we've summarized a complex experiment into the random variables PDF, and now we've summarized the entire PDF using the expected value, and then the question becomes, how do we compute expected values? Well, we have a formula, but if we can compute expected values more easily in a more convenient way, well, that's the law of total expectation. Well, that's a very important thing, because expected value is very important. It tells us what to expect from an experiment on average. Okay, so the law of total expectation says that we can compute the expected value in a similar way by weighting conditional expectations. Can compute expected value by weighting conditional expectations in a very similar way to computing a probability by weighting, conditional probabilities. So let's look at the expected value of my random variable x. Okay, and we just take the definition. It's equal to the sum over the possible values of x times the probability of x. Okay, but now we use the law of total probability here. Okay, the law of total probability says that the probability that big X is equal to it takes on some value, okay, is equal to the probability that big X is equal to x given A times the probability of A, plus the probability that big X takes on the value x given not A times the probability of not A. Okay, that's the law of total probability. So, okay, we can expand this as the sum over the possible values x times. Now here we have the probability that big X equals x, so we can expand that using the law of total probability. That gives us the probability that the probability for x given A, that's this guy, times the probability of A, plus the probability of x given not A times the probability of not A. Okay, so I'll just draw a line here. Okay, I just expanded this using the law of total probability, which is equal to, okay, now I'll separate out the terms and I'll look at, this is a sum over x, so the probability of A is a constant, so this is the probability of A times the sum over x probability of x given A, plus, okay, using the addition rule, I can take the sum of this guy plus the sum of that term, plus the sum over x times the probability of x given not A, okay, and I can pull the probability of not A outside the summation times the probability of not A, which is, this is the expected value of x given A. So this is the expected value of x given A times the probability of A, plus the expected value of x given not A times the probability of okay, so let me shift, I've run out of room here. So this is equal to the probability, so the probability of A times the expected value of x given A plus the probability of not A times the expected value of x given not A. Okay, so let's make sure that we all agree with that. Probability of A, this is the expected value of x given A. That's the definition. Okay, and then probability of not A, the expected value of x given not A. So the expected value of x given A is just, you weight x by the probabilities of x given A. Okay, the expected value of x given not A, you weight x by the probabilities of x given not A. That's all it is. Okay? And you'll see the similarity between this formula for the expected value of x. You take the conditional expectations for the two cases, okay, and weight by the probabilities of those two cases. For the probability that x equals little x, so for the PDF of x, you take the conditional probabilities in your two cases and weight by the probabilities of the two cases. It's the exactly analogous formula of the law of total probability, but now applied to expectations. So this is the law of total expectation. Okay, so I'm going to write it there, okay, and box it. So the expected value of x is equal to the expected value of x given A times the probability of A plus the expected value of x given not A times the probability of not A. Okay. Bam. This is the law of total expectation. Okay. And let us put that in a red box. Okay, so that's the law of total expectation that allows us to compute an expectation using conditional expectations. Okay. And we've now just discussed conditional expectations. So let me show you the example with height. Okay. So I'll erase here, and then we'll do a bunch of other examples. So, according to the law of total expectation, the expected value of height should equal the expected value of height given man times the probability of man. In other words, if you randomly picked a person, what are the chances it's a man? Plus, so this is case 1. So this is the case A. Okay, plus the expected value of height. Now we need to consider the case not man. Well, if it's not man, it's woman. Given times probability of woman. Okay, now I'll fill in these numbers for you. So the expected value of height given man is 69. Okay, the expected value of height given woman is 64. Okay, the probability of a man, okay, now that turns out to be approximately 0.49. And the probability of a woman is approximately 0.51. So there are slightly more women in the US than men. So 49% men, 51% women. And when you compute this times this plus that times that, indeed, you will get approximately 66.5 inches. Law of total expectation. Let's do another example. Example. Okay. So a box, an opaque box, contains 10 coins. 10 coins. Okay. And the 9 of them are fair. 9 fair. And 1 is biased. Okay, it has 2 heads. So you pick a coin and flip it 10 times. So pick a coin. And what do we mean by pick a coin? Randomly. And flip 10 times. Okay. And we're interested in the number of heads. Number of heads is x. Now, you can sit down as an exercise and compute the PDF for the number of heads. So you have to consider, all the possible outcomes. You can do the outcome tree. Either you get, a biased coin or you get a fair coin. So that's the first branch in this experiment. And then you flip 10 times. So you get a sequence of length 10. And we're interested in the number of heads, and you can do all that. Okay. But I'm going to show you how easy it is to compute the expected number of heads using the law of total expectation. So the expected number of heads, so the expected value of x is equal to the expected value of x given the first case. So now you have to have a little bit of creativity in sort of deciding what's, the first case and then the complement of the first case. So this is like case by case analysis of expectation. So what's, A? What's case 1? Well, we can say given that you picked a fair coin. So if you times the probability that you picked a fair coin. Okay, that's case A. Okay, plus the expected value of x given now the complement of fair, the other case. Well, not fair means you pick the biased coin. So biased times the probability that you picked a biased. Okay, now let's fill in the numbers. So this guy here is 9 over 10 because you pick a coin randomly. So the chances you pick a fair one is 9 out of 10. It's a uniform sample space. 9 of the outcomes are fair. 1 of the outcome is biased. Okay, so 9 out of 10. And what's the expected value of 10 flips of a fair coin? Well, that's 10 times p, 10 times a half. Okay, so this here is 10 times 1/2. Because this is exactly a binomial. I'm doing 10 trials, and each trial has a success probability 1/2, where success is defined as I got a heads. Okay, now what about here? Biased. This is 1 over 10, the chances of picking the biased coin. Okay, and the expected value of the number of heads given that you picked a biased coin, well, it's 10 times p, but p is 1, because if it's biased, the probability of success is 1. So this is 10 times 1, okay, because the probability of success is 1/2, the probability of success is 1. So what do I get? I get 5, so I get 5 times 9 over 10, so I get 5 times 9 over 10, plus 10 times 1 over 10, 10 times 1 over 10. So this is equal to 10 times 1 over 10 is 1, and this is 4.5, 45 over 10, so 4.5 over 10 plus 1. So 45 over 10 is 4.5, so 5.5. Yeah, interesting. Okay, so if I pick from 10 coins, 9 of which are fair and 1 is biased, I pick randomly and then I flip 10 times, I will expect to get 5.5 heads. It doesn't mean that when I flip it, I'll get 5.5 heads. Sometimes when I do this experiment, I'll get 0 heads, 1 head, 2 head, 3 head, all the way up to 10 heads. Okay? And this is if I repeated this whole experiment many, many times, on average, I will see 5.5 heads. Okay? That's what to expect when you do the experiment. That will never actually happen. Okay? So that's expectation. Now, if we have time, let's do a cute application of the law of total expectation. Let's do this.